Okay, this is going to be a follow-up to what we just did with the covalent compounds and finding boiling point, freezing point. There are two types of compounds, as we've talked about at least. There are covalent compounds, there's ionic compounds. Covalent compounds do not break apart as a rule. I mean, they're not completely 100% true, but enough for us to concern ourselves with right now in Chem 1. Ionic compounds will fall apart, will break apart. Now, again, this is another one of those situations where not all ionic compounds completely fall apart. There's a certain number that will, a certain number that will not. And we're going to talk about both scenarios, but we're going to start off with a complete dissolving of ionic compounds. Now, to discuss what happened with the covalent compounds, we said the boiling point of a covalent compound is the original boiling point. And when you add stuff like a compound that's going to involve water bonding to it, it's going to increase the boiling point because it's going to take longer for the vapor pressure to equal the atmospheric pressure, which is the definition of boiling point. So what we used here is an increase by a factor of what we call the boiling point elevation constant, which will have to be given to you, times M, which is the molality of the solution that we have. And for freezing point, covalent, we start off original freezing point, and we're going to lose temperature. It's going to take a while for it to adjust itself and get the crystals aligned just right. And it's instead of using KB, we're going to use KF. And again, we multiply that by the factor that is the concentration of the solution. So what happens if you get more particles in solution? Let's take the most common ionic compound that we deal with, which is sodium chloride. And let's look at the dissolving reaction. We did this a while back, but we're going to do this again because this is pertinent to what we're going to be talking about in just a little bit here. If this is going to dissolve in water, and in Chem 1, all our solutions are going to involve a solvent of water. Now we get into Chem 2, if you are so inclined to join us at that next level, we will be getting into other solvents. But for right now, we're just going to talk about water. When you dissolve this in water, this breaks down into sodium positive ions because sodium is a group 1 metal and gives up 1 electron, hence the positive 1 charge. And chlorine is more than happy to take that extra electron and make it a full 8 electrons at its outermost level to form the chloride ion. And they're both aqueous because the water is attaching itself to that. Now, this is going to cause a more widening of the range from for boiling point and freezing point because you have more water involved in the bonding here, which means it's going to take longer for the water to break apart, to come off as water vapor, and it's going to take longer for the crystals to form because they're more involved in the bonding with the ions than they were with the covalent. So we have to throw in a factor. Now, if you take a look here, all the covalent compounds here, they just broke down, they did not break down, the entirety of the molecule was attached to water. So that you have basically 1 particle that has been created in the dissolvent. In this case, you have 1 of these, and you have 1 of these ions, and now you've got 2 particles in the solution that the water is going to bond to. So what you need to do here is understand that this is going to double this part of the equation. We call this quantity here I, and that stands for the Van 't Hoff constant, named after a Dutch scientist who came up with this idea brilliantly. And so we are now going to say that the ionic boiling point is going to be equal again to the original boiling point which of course is for water is 100 degrees Celsius, plus still we're going to have our Kb, and plus again because it's going to elevate it, make it higher, times the molality, the original molality of the entire solution, times that Van 't Hoff constant, because it's going to double this factor right here. Okay? And then the freezing point is going to drop in the same fashion. So we're going to have the original freezing point minus Kf times M times I. So these are the two new equations that we are going to be dealing with in calculating these boiling points and freezing points. So the example in the notes that I gave you is we have a 3.50 mole per kilogram solution of aluminum nitrate. And I want to know the boiling point and freezing point of this solution. So we have to start with the dissolving reaction. And the dissolving reaction is going to give us our value of I. And that's going to be plugged in right here. And our molality here, M, is our 3.50. And of course, this is 100 and this is 0 degrees. And we're going to throw all that stuff in there to see how this is going to be affected. But the first thing we need to do is find that I. So do the dissolving reaction for aluminum nitrate. Being an ionic compound, solid at room temperature, this dissolves in water. This is going to give us aluminum. Aluminum is a metal, group 3A on your periodic chart. Therefore, we'll have a charge of 3 positive. Nitrate is a polyatomic ion. You go to your polyatomic ion chart, find NO3, find the charge for that. It's -1. And we have 3 of them. So this 3 is going to go in front. And remember, once it's attached or detached from the compound formula here, we no longer need this parenthesis. So we just put NO3 negative and the negatives for that. Now, the Van 't Hoff constant then is going to be equal to 1 for the aluminum and 3 for the nitrate, for a total of 4. All right? So the boiling point is going to be 100 degrees Celsius plus the original concentration, which we said is 3.50 moles per kilogram, times, the K, I should have probably put the Kb first, which is 0.512 degrees Celsius per mole per kilogram. It does make a difference, since multiplication is commutative. And then our I value here is 4. And then if you punch that all out into your calculator, you get, and round out to 3 centimeter figures, 107 degrees Celsius. Okay, so that's the boiling point. The freezing point, the original freezing point is 0 degrees Celsius, and now because it's going to drop, because you add this stuff in there, the solute, that breaks down into 4 parts, this is going to equal to the Kf, which is 1.858 degrees Celsius per mole per kilogram, times the molality, which is 3.50, times the I Van 't Hoff constant 4. And multiply this out, round out to 3 significant figures, you get negative 26.0 degrees Celsius. And that's how you determine the new freezing point and boiling points of the solution. You throw stuff into water, you are not going to get 0 degrees to 100 degrees. If you're to boil water from your tap at home and you have a thermometer, you'll find that it doesn't boil at 100 degrees. It boils at slightly more than 100 degrees because tap water is filled with all kinds of garbage. Well, kind of is and kind of not garbage, but you don't understand. Okay, so one of the things I was saying in the introduction is that some compounds don't break down completely. Now, we're going to not really examine this too closely in Chem 1. We talk about Chem 2 a lot. But I want to show you what effect it has on the Van 't Hoff constant that will tell us if we have a compound that is completely broken down or not. So let's take this scenario that I've also included into your script. We have a 1.75 mole per kilogram solution of some unknown. So I don't even know if it's ionic or covalent. And that's really not the point. What we're trying to find here in this problem, if we are told that the boiling point for this thing is 100.675 degrees Celsius, then what is the value of I? And we'll have a pretty good idea if this is a complete dissolving compound or not. Obviously it's not, because otherwise why would I introduce it that way? But let's see how we can tell. So we're going to take the boiling point formula for ionic compounds, and introduce the I to see if this is indeed going to happen here. So we got 100.675 degrees Celsius is equal to the original boiling point, which is 100 degrees Celsius. The Kf here is Kb rather, is 0.512 degrees Celsius per mole per kilogram, times the molality, 1.75 moles per kilogram, times our unknown I. So now, if I multiply those two together right there, I get 0.896 degrees Celsius, the moles per kilogram cancel out. Okay, so now I have just a basic algebra problem. I'm just going to cross this out and not get confused by that. This is 0.896 degrees Celsius times I. So I subtract 100 on both sides, degrees Celsius, and I get 0.675 degrees Celsius is equal to 0.896 degrees Celsius times I. And then we're going to divide both sides by that 0.896. These cancel out, degrees Celsius cancel out, and this gives us no label for I. I has no label. We can say particles, which is fine, but it's not introduced into this equation in that form. And so we find that I here is 0.753. Now, that's a pretty small number. That's less than 1, and that tells us that this is not a complete dissolving reaction, which means it's most likely, but not necessarily, but most likely is going to be ionic, but we don't really know. All we care about is this. In fact, if you compare that to the original concentration, which was 1.75, and if it was ionic or covalent, that would be times 1. But we'll just say I is 1 and then go from there and make our assumptions from that. And then turn that into a percent, so multiply by 100. And it turns out that this is going to be 42.9%. So that means if it was a covalent compound, then this is only going to dissolve 42.9%. If it was covalent, ionic, it would be less than that, because there's more parts being broken down. So this tells us that this is a pretty incomplete dissolving. So this is how you find your unknown I based upon what we have there, using the same formula, just working backwards, just like our regular algebra problem. Algebra is just simple arithmetic done backwards. So that leads us up to our practice problems. We have 5 of them that are both types of problems that we just dealt with. So have fun.